Hi. I wanted to follow up on something I kind of glossed over in the previous video about compilation. Last time I talked about how the compiler takes code written in a relatively, English-like language, a high-level language like C++, and it translates it into machine code, right? So that's true. That's what it does. But if you take, like, let's say you write a small source file called hello.cpp, right? And you run it through a compiler. So you run it through cl.exe on Windows, or you run it through something like GCC on Linux or Mac. What you'll see is there's actually two new things that you see. So you do get hello.exe, right? You get your executable program that you can run, but you also get hello.obj. And so that's kind of what I want to talk about. So what's really going on is there's two steps there. So you might think that it's hello.cpp becomes two things, but that's not actually the case. What happens is more like this. So we have hello.cpp, which becomes hello.obj, and then that becomes hello.exe. So what's going on here? So what's happening is the obj file is an intermediary file. So what it is machine code, but it's not a full program. So you can kind of think of it as a fragment of machine code. That's what the compiler does. And then there's this other thing, or this other step, called linking, or sometimes done by a linker, right? And what that does is it collects one or more sort of fragments of a program and makes it into an executable file. So what's going on here is there's kind of like three steps, right? So when we go from hello.cpp to hello.obj, that's compilation. When we go from hello.obj to hello.exe, that's linking. So why is it two steps? Well, in this case, it doesn't really make sense, right? We have just one file, and we're doing kind of two things to it. But if we have more than one file, which is almost always going to be the case, it starts to make a lot of sense. So let's say that my program is a little more complicated, and let's say I'm making a game, and let's say this game's about ogres. Maybe you fight ogres, or maybe you make friends with ogres. Who knows, right? So I've got maybe I would have ogre.cpp. So that would become so in this case, it's still pretty simple, right? This is still way simpler than any real application would be, but we have two source files. We have ogre.cpp and hello.cpp. So let's say hello is our main program, and ogre implements something about ogres, right? So when we compile it, we get obj files, right? And both of these files, so hello.obj is the result of taking hello.cpp and translating it into machine code. Ogre.obj is the result of taking ogre.cpp and translating that into machine code. And then they get linked together into hello.exe, let's say, right? So the reason for that is compilation can actually take a long time, right? So what we want to do is, as you work on a program, a game, or anything else, right, it's highly likely that you only work on a small portion of the code at a time. So even in this really simple example, I've got, let's say hello.exe, cpp, sorry, is my source file for the main application. And then ogre.cpp is my source file for ogre stuff, right? So it's any given moment, I might be working on something that only is implemented in the main application, or I might just be working on something that has to do with the way ogres work. And that's really important, right? So part of being an engineer, a huge part of it is breaking really big things into components and doing that well, right? So, starting to work with things in a modular way and to build things in a modular way. So it's really important to break up your code. If you if you tried to implement anything interesting or to scale as a single CPP file, you'd be in for a really bad time. You might be able to do it, but if you did it, you'd end up with something that was just completely unmaintainable, right? Because you'd end up, you want to make a little change, and you'd have to dig through, you know, tens of thousands of lines of code, possibly. That's really brittle. That's really hard. It makes it almost impossible to work with other people. So it's just not done. Don't do it, right? So what you want to do is you want to break up all of your functionality into relatively small size chunks. And you want each chunk to be its own file, usually. And you want each of those chunks to have well-defined roles, right? So let's say I spend, weeks working on, well, not weeks. Let's say I've spent 5 hours working on Ogre.cpp, right? Now I want to recompile my game and see if my changes work, right? But I don't want to recompile hello if I didn't change it, right? So what happens is modern compilers and linkers are smart enough to know that the hello.cpp file didn't change. So when we run the compilation step, what'll happen is ogre.cpp changed. So it gets recompiled. We have a new ogre.obj. But we still have the old hello.obj. So what we can do is we don't bother recompiling hello at all because it didn't change, right? So we take the new ogre.obj and the old hello.obj and squash them together to get our hello.exe. So that's really important because if you had to, compilation is already something that can take a lot of time because it's a very complex thing. You're taking, a lot of code, possibly, right? In small examples, compilation happens like that. But when you're working on a large project, compilation can easily be a multi-hour thing. You might have to walk away for 8 hours or more for something to compile. If you're talking about something on the scale of, a huge, huge project like a Skyrim or, Fallout, stuff like that, right? So it can take a long time. But as you're working on stuff, you generally need to tweak and test and iterate, right? So being able to only recompile parts is really important. And one of the ways that we get to do that is by compiling parts and then having this other step, the linking step, that takes stuff together. So that's one big reason why we have compilation and then linking. The other big reason is that, generally you're not going to write everything yourself. So what we've got here is, we've got kind of 3 realms, right? So this top here, we have source code. Now that source code is human readable. I know, it's syntax can be confusing and everything, but it's essentially human readable, right? So, when we're up here, we're talking about something that's basically, it just is C++ source code, right? Now, in this middle layer, we have compiled stuff, right? So this is machine code here. It's no single part of this is a full program, but it's all machine code, right? So this is stuff we can read as humans. This is stuff the computer can read, and then down here we have something that the computer can run, meaning it has all of the necessary components. So, it's kind of like, think of this stage as sort of like parts of a car engine. So, we might have like a carburetor, and we might have a timing belt, stuff like that, right? Each part is necessary, but it's not until we put them all together that we get an engine that we can start, right? So when you're working on big projects, you're not going to write everything yourself. You don't want to do that. That's not a good way to approach things, right? Because you don't want to reinvent the wheel. So there's some key engineering concepts. One thing you'll hear is dry. Don't repeat yourself, right? Meaning that if you've got functionality you need to implement it once and then reuse it, rather than implementing it in multiple places. Similarly, you don't want to reinvent the wheel every time, right? So one of the things you end up doing is slightly related concept or issue is that C++ in and of itself doesn't really do much by design. So the language itself only really does things like memory management and a few other things, right? So everything else is additional libraries. Now a lot of them are standard. So anytime you're writing C++, you have access to a lot of standard libraries, but they're not included by default, right? In your program, because every program needs to do slightly different things. right? So if let's say you're writing a program that does music synthesis, right? So there's things you'll need to do. You'll need to be able to talk to a sound card. You'll need to output audio, right? And that's really important if you need to do it, right? You might be writing a piece of financial software that needs certain kinds of financial math implemented that is only really used if you're doing financial software, right? You might need to output stuff to the terminal, to the screen. You might need to get stuff in from the terminal, right? But that doesn't really make sense if you're building a game that's just mouse and keyboard, possibly, right? So anyway, so you include different components, right? Now those components are pre-compiled because you don't want to deal with recompiling everything, right? So they exist here in this layer, right? So that's really good. So you don't have to recompile everything, right? So when we pull in precompiled libraries, they exist kind of here, or they can exist here. You're not gonna usually, so there are exceptions to every rule, right? But you might get third-party stuff here. If you get third-party stuff here, that's going to mean that you got the source code from somebody. Now you could do that, right? But you only want to do that if you mean to change the source code. So, like if you work with Unreal, you can get access to the Unreal Engine source code, but you generally don't dive into that unless you really need to. So you might operate on third-party stuff at this level, but usually you don't, right? Usually this layer of source code is just your own content. But you'll generally always have at least some libraries that you're getting from other people that exist here as precompiled stuff. You might also have third-party stuff that exists here. So where that comes in is something called, on Windows it's called a DLL. On Mac or Linux it's called a .so file. But the Windows version is a good hint as to how it works, right? So on Windows they're called a DLL, right? And that's short for Dynamically Linked Library, right? So Opengl is one example. So what we have is, like, let's say OpenGL stuff. Okay, so OpenGL, right? So if you're gonna write a 3D application or game, just come back to that in a second actually. So you don't want to reinvent the wheel, right? So you're not going to start by writing your own graphics driver and display code, probably, right? I mean, you can do it if you want as like a learning experience, but generally you don't want to do that. So what you'll generally do is you'll use a graphics library, the two biggest being DirectX and OpenGL, right? So what they do is they're low level, right? They do things like let you render a triangle at a given position, right? So that, they do very, very basic things. OpenGL does not, make a game level for you, right? It's not a game engine. It's lower level than that. But it does do a lot of stuff that is very common to anything that wants to deal with 3D or 2D graphics. So what happens is everything that gets linked is inside the executable, right? So, we have our source code. We might have other people's source code. We have our compiled version of our source code. We might have other libraries that have gotten included. So third-party libraries. So there might be third-party libraries. So I know that's probably hard to read, but we might have third-party library, a third-party source in this, this layer here of source code. We might have precompiled third-party libraries here, and sort of the post-compilation layer, and those all get included in our executable, right? So they get bundled together. Now, with really, really generally applicable stuff like OpenGL, right? You don't want to re-include that every time, right? It's kind of just accepted that there's anyone that uses a computer, it's highly likely that they're going to expect to do something involving 3D graphics, right? So rather than have every program that uses OpenGL contain OpenGL, all the implementation for that system, there's something called just the OpenGL DLL, right? So what happens is you get an executable that makes use of OpenGL, Now you do have to still include some stuff in the compilation process and linking process so that it can talk to OpenGL. But OpenGL also exists on your system as a DLL. So what a DLL is it's basically a program. It's an executable program, but all it's there to do is really to be part of other programs. So it's an enabler of other programs. So what happens is when this runs, it can talk back and forth to OpenGL's the DLL and make use of OpenGL, right? So why do that, right? Well, the reason to do that is the functionality in the OpenGL DLL only has to exist on the system once. It only has to be there once, and it can get used by anything that needs it, right? So so there's DLLs that happen too, and they get dynamically linked, meaning that they're not linked during the compilation and linking. They're dynamically linked at runtime, right? So that's what DLLs are. Right? That's maybe getting a little bit into the weeds, but the upshot of all this, right, is what I wanted to get across is when you compile stuff, you'll see this whole process, right? So you're really compiling. You go from source code to intermediary files, and then those get bundled together into an executable, and that process is called linking. So compiling source code to machine code, and then machine code, one or more components of machine code get linked together into an executable, or possibly a plugin like a DLL, right? Yeah, so you'll see OBJ files. They don't really matter that much. If you delete all your OBJ files, all that's going to happen is you'll have to start compilation over from scratch, which in small projects doesn't really matter, right? So you don't have to worry about them too much, but understanding that there's compilation and then there's linking is pretty important for just understanding what's going on, right? So that's kind of what I wanted to talk through. So hopefully that helped, and yeah, see you in the next video.